This week we're looking at growth curve models. So first, let's just get out of the way. What are growth curve models? Growth curve models allow us to assess change over time. And HLM provides great tools for assessing change over time because we already have this structure in HLM where we're thinking about units at two different levels. We're thinking them as individual observations nested within clusters. And so we're thinking about how, in growth curve modeling, how change within the clusters happens over time. So we have multiple observations for each cluster that happen at different time points. An alternative approach to growth curve modeling uses the SEM framework. And SEM, I believe, will be offered next fall, and it's typically taught by Dr. Chem as well. The results are actually very comparable, and the method is more comparable than you might think as well, though each approach does have some challenges and benefits associated with it. In our data, we're going to be looking at the depression.csv file, and this is a longitudinal data set which examined participant depression ratings over time. This was part of a drug trial or something similar to that, and so they were looking at two different antidepressant medication-related metabolites in participants' bloodstreams as well as their depression over time. And there were 4 time points that were assessed, and they are weeks 1 through 4. So the steps for assessing a growth curve model, and this is again sort of Dr. Chem's procedure, it's not necessarily the only procedure that you can use, but it is definitely a good one, is we start by checking the ICCs, which we're going to skip here because we've done that. Then we have to decide where we're going to center time. Then we visualize the growth curve as it appears in the data, fit our model, and then add additional predictors. So skipping the ICCs part, now we have to decide the time metric. And time variables are somewhat unique in that they make the conditional intercept sort of meaningful on its own. So we don't really want to center at the mean of time. That would mean that our conditional intercept represents the exact midpoint in our longitudinal study. We want to center our time point somewhere where we can think of it as being a meaningful baseline. So this is going to be the point where we compare all other time points to this point. This will often be time 1, where you compare all subsequent time points to time 1, but you can think of other scenarios where you might consider other time points the baseline. For example, maybe you think the last time point is the baseline, and you want to compare all the previous time points to the final time point. So here in our data, we're going to check the timing metric, and note that for some reason the ID column, a variable name in this data loads up a bit weird. If you can just run this line of code to rename it ID. I'm not sure what's going on there. Sorry about that. But here, so I'm going to check the frequency table of time observations. So we see we have 66 observations for each of weeks 1, 2, 3, and 4. So that tells us this is a balanced data set. Each participant was observed at each time point and across 4 different weeks. But note that the time metric goes from 1 to 4. So that means the intercept is currently outside of our range and not actually interpretable. So we want to recenter this, or we want to shift this time variable so it has a meaningful 0. So if we want to center at week 1, we can just subtract 1 from the week variable here, and here I created a new variable called time, and now we see that the time variable goes from 0 to 3, so 0 is the baseline. And then we're comparing all subsequent points to week 1. If we wanted to center at week 4, we could do that as well, just by subtracting 4. And here we see all the first 3 time points get negative numbers, and the last time point gets 0. And this would compare all of each of the first 3 weeks to time 0. To me, in this data, comparing points to week 1 makes more sense. So we're going to do that for the rest of this example. I just wanted to demonstrate how you center at different time points. So this should be pretty straightforward at this point, but let's just double check. What level variable is time? Is it level 1 or is it level 2? So because participants are the clusters in this data and have multiple observations, time is level 1. Now, maybe a slightly trickier question is, do we need to think about contextual effects for time? We've talked a lot about thinking about contextual effects for level 1 variables, but is this something that we should think about with time as well? In this case, we definitely don't, and the reason is because the time assessment is balanced. So all participants will have the same mean value for time. So after we center going from 0 to 3, the mean time point will be 1.5. In unbalanced designs, where not every participant is observed at each of the same time points, there will be between cluster time variability, but that's more commonly going to be an artifact of the design and not really an intrinsic feature of the clusters, which is why you get contextual effects. Another way to think about this is, unless there's some reason you think that certain clusters are more likely to be observed at certain time points, you shouldn't have to worry about contextual effects. And if you check for contextual effects and you find them, it's more likely going to be some kind of random noise than it is something meaningful in your data. If you do have some sort of self-selection into time points, this may be more of a missing data problem in a sense than a true contextual effect, but that's something that we'll talk about a little bit more as we go. So because time is at level 1, we want to look at both the average effective time across all participants in the aggregate pattern, and then as well as individual clusters to make sure that we look at our random effects correctly. So we can visualize the average pattern with the profile plot. This is going to be new. And then we can look at the cluster level variations with the spaghetti plot, which is like what you've seen before. So we will look at one new variant. So for the profile plot, what we first want to do is summarize the outcome using time as a grouping variable, and we can do this with the summary SE function from the rmist package. We briefly looked at this in lab 2. Note that we specify na.rm equals true, or else we use listwise deletion. There is some missing data in this data set, and we don't want to delete it listwise. So here we see the output of the summary SE function. It just gives us a table with the depression scores averaged at each time point, and it gives us the standard error and confidence interval as well. And then we can plot the depression score at each time point just using ggplot the way we've learned. We're creating error bars here using the confidence intervals, and this will give us a nice plot that looks like this. So this tells us the average change over time for each time point as it's observed in our data, not modeled, just the actual observed averages for each time point and how they change. For the spaghetti plot, we're going to do exactly the same thing that we've already done. We're going to select some clusters, and then we're going to look at each of their slopes. So here is some code that's very similar to what you've seen when we've produced the spaghetti plot. So this gives us regression lines for each participant. You can see the regression lines kind of move in different directions, so this definitely looks like random slopes to me. You can also sort of do a hybrid spaghetti profile plot where you look at the actual observed data for each participant over time. It's a little bit harder to see what's going on with something like this, but it's also a little bit more true to the data. So here you see this is just each actual time point observation for each participant. And it's a little bit harder to infer whether these are random slopes or not, since they're a lot more jagged. But you can sort of still tell that some of the lines go in different directions than other ones overall.